So what are we going to talk about now?
So now let's talk about how you get from the Nernst potentials of the ions to figuring out the membrane potential with its multiple ions.
That's right. And that multiple, because the membrane may go through different potentials. At rest, it's at the resting potential. At the peak of the action potential, it's something else. We'd like to be able to put those all together in some meaningful way. And we know that the two key things are concentrations, in and out, and permeabilities to the ions. So,
okay, so let's start. So here are the three main players.
Good. And in the switch ion axon, where does the membrane want to sit if it was only permeable to one of these?
So the Nernst potential for sodium in the squid giant axon is about plus 55.
Good.
Potassium, it's about negative 75
Good.
millivolts. And chloride is negative 60 millivolts.
Good. Okay, so where do these numbers come from?
From our Nernst potential equation.
That's right. So let's put that together. That's the natural log.
This is our ion out.
Right.
Over ion in.
Perfect.
Okay.
That's the general form. Good. Now Z for sodium is just 1, so it's fairly simple. And potassium. But for chloride, it's minus 1. All right,
and so it's flipped.
So that's going to flip the ratio. Okay.
So when we're talking about the membrane as a whole, because it's permeable to all of these ions, there's probably this ratio in our equation.
That's right.
So let's start with that ratio.
Okay.
So sodium out over sodium in.
Right.
We've got our potassium out over potassium in.
Okay.
And then because chloride has a negative charge, again, the Z, I'm going to flip it.
Okay.
Because we're going to put all of this in a log, just like the Nernst.
That's right.
So chloride in over chloride out.
Good. So we have the pieces, the players, and now we have to weight them by the permeability. So what do we do?
So we want this to be weighted so that, let's sort of theoretically think, if we had just sodium. So the sodium had a high permeability, and the potassium and chloride had no permeability.
Right.
We'd want it to end up. We want the membrane to end up resting at the Nernst potential.
Right. So
we
want the whole thing to reduce back to that.
So let's put the permeability on the top and the bottom.
Why do we want to do that? Well,
let's see. So if this would weight the permeabilities.
And if everything else, all the other permeabilities is 0, what would happen to that ratio of this to that?
It would cancel out and be 1.
That's right. So you would reduce to what you wanted, which was just the Nernst potential for that one ion. Good. Okay.
That's okay.
Right.
And then to sort of combine them, we're going to
sum them up. And then outside here we have...
This is probably still following the laws of...
That's right. Well, actually, if we did the derivation and took into account the fact that these are independent ion fluxes, we're at steady state, across the membrane there is a constant field, and the partitioning of ions into and out of the membrane is the same, all of those assumptions allow you to actually write down the equations that when you solve give you this, which is...
This is the constant field equation.
Or Goldman Hodgkin Katz, after the people who first described it. But yes, this is the constant field equation.
Okay,
Good.
So let's look at how this works now.
Yeah, let's again get an intuitive feel. Let's first talk about the resting potential.
Oh, wait, let me first go over again. So
yes, good.
If it's only permeable to 1,
right,
we've set it up so that the constant field equation will spit out basically the Nernst potential.
Exactly. So if potassium was the only one that pK was, the permeability was non-zero, the other terms would just cancel out.
And this would go
and then pK1 plus over pK plus is 1, and you just be RT over F ln potassium out over potassium in, and that's just the Nernst potential. And that's where the membrane would sit. Good. Let's do the resting potential.
So at the resting potential, that's what? Negative 60?
So what does that mean in terms of the chloride from what we just said?
Well, we know that there should be a high permeability.
Probably yes, but in fact, no matter what the permeability is, you're actually sitting where it would like. So you could be very permeable, you could be not so permeable, it won't do very much because you're sitting at close to its Nernst potential. Good. What about sodium versus potassium?
Well, let's see, negative 60 is a lot closer to negative 75 than to plus 55, so we can probably assume that the sodium is not having a strong pull, and the potassium is having a strong pull.
So that if you did the ratio of the permeability of potassium to sodium, it would be a large to a small number.
I'm just writing that these arrows are the permeabilities.
Good. Now, and this is the last thing we need to think about right now, let's say we're at the peak of the action potential. What value is that?
Is that about negative, or about 30, right?
Plus 30 millivolts. Okay, so now again, look at our Nernst potentials, and what does that tell us?
Well, we're much closer to 55 now than negative 75.
That's right.
So that's probably because our permeability to sodium is high and potassium is low.
And that's exactly how the action potential works. So the constant field equation gives you some intuitions about how that works, and it's actually completely accurate over the entire range. If you have the permeabilities and you have the concentrations out and in of the ions, it will tell you what the membrane voltage is.
Okay.